We talked a little bit about ions in terms of electron configurations. We know that anions form when atoms gain electrons. So then we're just going to add electrons to the electron configuration, and that usually causes no problem. For cations form when the atom loses electrons, so we need to subtract electrons. And this can get a little bit tricky. So the main group elements, the main group cations, main group elements tend to follow nice patterns. You just remove those electrons in the reverse of the filling order. So looking at aluminum, a main group metal, here is the electron configuration for the atom. So for the aluminum ion, we're going to start at the end and remove 3 electrons. So we're going to get rid of that one and those 2. And then what we've got left is this for the electron configuration of the ion. The transition elements like to be different, and so we need to think a little bit more for them. Here is the electron configuration for iron. Which ones are the valence electrons in there? Well, it's really tempting to say the 3d6 because that comes at the end, right? And those are the highest in energy.
4s2.
But the 4s2 are the valence electrons. So valence electrons have the highest principal quantum number. So looking at the electron configuration, we're looking for the largest big number, right? So there's 1, 2, 2, 3, 3, 4, 3. 4 is the biggest number. That corresponds in the hotel analogy to the 4th floor. The valence electrons are the ones that are on the highest floor that has electrons staying in rooms. So the valence electrons get lost first. And I think of this as a tornado comes along. I grew up in the Midwest with tornadoes, not earthquakes. Tornado comes along, and it's going to take off just the top floors of the building. So if these guys are staying on the 1st, 2nd, 3rd, 4th, 3rd floors, and we lose the top floor, who are we losing? We're losing these electrons on the 4th level. Those are the valence electrons. Everybody in the floors beneath are core electrons, and they're going to be okay. So those are the valence electrons. The valence electrons get lost first. So what we're going to do is we're going to take those valence electrons out for the Fe2 plus cation. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. We just got rid of that one. If we want to make a positive 3 cation, then we need to lose 1 more electron. And now we've gotten rid of the original valence electrons. Now we can just go in reverse order of filling and get rid of one of these. So we have 3d5. Any questions about that? Transition elements, you lose the valence electrons first. Those are those s electrons. Magnetic properties. Some atoms or ions will be attracted to a magnetic field and others will not. So an atom or ion is paramagnetic if it has unpaired electrons. Those unpaired electrons, they're spinning charges, those generate a magnetic field. That magnetic field interacts with the other magnetic field. Diamagnetic atoms or ions have all their electrons paired up, and so you can think of those paired spins as kind of canceling each other out. They don't generate a magnetic field, and so these sorts of atoms are actually slightly repelled by a magnetic field. So we've got paramagnetic and diamagnetic. One has paired electrons and one has unpaired electrons, and this one gets messy, at least in my mind. So what bothers me is that prefix para sounds like pair electrons, right? But that's not the way it is. But di means two, right? You heard the story about Noah's Ark? How did the animals enter Noah's Ark? 2 by 2, right? So di means two. 2 by 2 by 2. In a diamagnetic atom, all the electrons are paired up like Noah's Ark's animals. Okay? Paramagnetic ones are the other. They have unpaired electrons. It's the unpaired electrons, those spinning charges, that interact with the magnetic field. So the diamagnetic, not attracted to a magnetic field, and paramagnetic, these are attracted to a magnetic field. Easy to get mixed up. Okay, write the electron configuration and orbital diagram for each ion and predict whether each will be paramagnetic or diamagnetic. So, doing electron configurations or orbital diagrams for ions, I think it's best to start with the atom and then add or take away electrons. So we'll just look at the valence electrons. So cobalt is in period 4. So we've got 4s, and then we're going to have some electrons in the 3d. So there's 2 electrons in that 4s orbital, and then there's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's for a cobalt atom. The electron configuration for that would be 4s2, 3d7. Positive 2 charge means we're going to lose 2 electrons, right? Which electrons do we lose? The ones on the 3rd floor or the 4th floor? Is the tornado going to come and just take out the 3rd floor, or is it going to take the top? It's going to take the top of it off. So these are the valence electrons, so those are the ones we're going to lose. Bye-bye. And then over here, it's those 4s2, those are the ones we're going to lose. So now we've got the orbital diagram and the electron configuration for cobalt 2+ ion. Looking at electron configuration, and technically that should have argon in front of it. So it's argon 3d7. It's hard to look at the electron configuration and determine whether all the electrons are paired up. But we can look at the orbital diagram. Are all of the electrons paired up? No. No. They are not 2 by 2 by 2. There's some that are not in pairs. So this is paramagnetic. Will it be attracted to a magnetic field?
Yes.
Yeah, because these little guys don't have a pair, and so they are going to interact with the electric field. I'm sorry, the magnetic field. Let's look at nitrogen. So for nitrogen, we've got valence electrons 2s and 2p. And there's 5 valence electrons, 1, 2, 3, 4, 5. And that's for the nitrogen atom. And And then the electron configuration for the nitrogen atom, which would be helium, 2s2, 2p3. Yeah.
So, would it be like reverse the Hund's rule, like when you're taking electrons off, you like take them in reverse order? Like they come off in reverse order that they do?
So from the main group elements, they come off in reverse order of filling.
Okay.
So just, yeah, last in, first out.
Okay.
The transition metals, they don't.
They hit something.
Yeah. So with the transition metals, you have to empty that valence shell first.
Okay.
You get rid of the valence electrons, and then it's reverse order.
Okay.
Yeah.
So you would take off from the paired electrons first, and then the unpaired. Or,
Yeah. So if you were taking more electrons off here, you'd take one of these paired ones out, and then the other paired.
And then go back.
Mhm.
Go through.
Yeah.
Okay.
Exactly like that. Because remember the analogy, this is a room with 5 beds, and if this guy left, this guy over here is like, oh, I can move over there and take my own bed, right? There's not going to be an empty bed when other people are sharing uncomfortably with strangers, right? So this is the nitrogen atom. It's got a 3- charge. That means we have to add 3 electrons to it. So 1, 2, 3. Then over here, those are going to go into the 2p6. And now we've got our ion. Paramagnetic or diamagnetic? Diamagnetic. They're all paired up. Forgot how to spell there for a minute. These guys are all paired up. Hey, any questions? Mm-hmm.
You're reading some like iron's like inherently magnetic, right?
Mm-hmm.
So is there a reason? Well, like, is that related to this, or is that some?
It is related to this.
Okay.
Yeah. So since you asked, let's look at that. So iron is 1 less than cobalt, right? So let's just do this. Let's say we're looking at iron now. And so, I don't want to do that. So that would be the electron configuration for the element iron. And you see all these unpaired electrons?
Mm-hmm.
That's paramagnetic. It will be attracted to a magnetic field. Yeah.
Like when I was old, I always say, it's like, they said iron, cobalt, nickel, or like, are those the only 3 that are just like, very magnetic, or are there more than
I don't remember
Okay.
off the top of my head.
Okay.
But if you play around with magnets and metal objects, right? Magnets don't stick to all metal objects, right?
Yeah.
And then, you get into things like steel. Well, now we've got a mixture of lots of different things, so then that gets a little more
Can you make
complicated.
any metal magnetic, or like you magnet?
I honestly don't know. Those are great questions. Yeah. Any other questions? Mm-hmm.
So you added the extra 3
Mm-hmm.
into the 2p because N has a charge of 3 minus.
Right. Yeah, and it gets this 3- charge because it got 3 extra electrons from another atom. So what about the sizes of those ions? Well, cations are much smaller than neutral atoms, like a lot smaller. Like, so here is lithium, radius 152, lithium ion is 60. It's less than half as big. You compare all of these, and there's about a 2-fold decrease in size, right? Okay, so let's think about it. Does this make sense? When you become a positive ion, are you gaining electrons or losing them? You're losing them, right? When you peel things off, do you make the object smaller or bigger? You make it smaller. So cations should be smaller. What's surprising is just how much smaller they are. And that, again, has to do with effective nuclear charge. Anions are a lot bigger than neutral atoms. You make an anion by putting extra electrons on it, right? So you would expect that it might be a little bit bigger. Well, it's actually a whole lot bigger. Like the oxide ion is twice as big as an oxygen atom. And again, the huge difference in size has to do with effective nuclear charge. So anions are bigger, cations are smaller. And then we can talk about isoelectronic ions. So iso means the same, electronic refers to electrons, of course, so the same electrons. So these 4 ions, sulfide, chloride, potassium, and calcium, they all have the same number of electrons. They are isoelectronic. They have the same electron configuration as argon. So they all have 18 electrons. Well, the negative ions, the anions, we would expect are going to be bigger, and we would expect the positive ions to be smaller. And what's happening here is we have a difference in charge on the nucleus. So sulfide has 16 protons, calcium has 20 protons. And so the 20 protons are going to attract the outer electrons much more strongly and pull them in, and so these are going to be a lot smaller. This is 99 picometers, and that one's 184. So we should be able to predict ion size, looking at the periodic table. The first two should be pretty easy. If you just think about, well, am I taking electrons off or putting them on? Right? So going from potassium to potassium ion, am I losing electrons or gaining them? You're losing them. Is that going to make it bigger or smaller? Smaller. So we would expect that the K plus ion is smaller, and that's not the one we're trying to choose. We want to choose the bigger one. Fluorine and fluoride. Here we're adding an electron, right? Which would make it bigger. So this guy's bigger. Calcium or chloride, at first glance, you're like, but they're different elements. How can I compare those? But here's calcium. Here's chloride. Calcium has 20 electrons. If it loses 2, it becomes the same as argon. Chloride has 17 electrons. If it gains 1, it becomes the same as argon. So these two are isoelectronic. So which one's bigger?
One with more protons? No.
The one that had electrons added.
Oh,
Right? So this one had electrons added, and this one had electrons taken away.
oh.
So the chloride is bigger. So let's go back to the actual sizes here. So the chloride ion is 181 picometers, and calcium is 99 picometers. Again, their electrons are in exactly the same arrangement, but here we've got 17 protons, and there we've got 20. And so 20 protons pull the electrons in and make it smaller.
So you wouldn't look at the effective nuclear charge then, you're just looking.
Well, you could, but since the, yeah, I mean, you certainly could. It'll give you the same answer as just looking at them.
Whether it's gaining or losing.
Yeah. Yep. So in order for an atom to become an ion, it has to gain or remove electrons, and there's energy involved in that. So the ionization energy, abbreviated IE, is the energy needed to remove an electron from an atom or an ion in the gas state. and this is always positive. So thinking about energy as money, in order for the atom to give up an electron, you're going to have to give it some money. You're going to have to pay it, put energy in to pull this electron away. These electrons don't just fall off. We can write an equation here. Whatever the metal is in the gas state plus some energy, we're going to get a +1 ion and 1 electron being removed. That's called IE1, the first ionization energy. That's removing the first electron. If we take this ion and remove another electron, that's called the second ionization energy. Also going to be positive, and the second one is going to be larger. It's like, well, I sold you that first electron kind of cheap, but now you want another one. I'm keeping track of trains. It's 140. So it costs more to remove the second electron. So there are trends in this, and this is related to atomic size. We see going down a group that the ionization energy gets smaller. As we're going down a group, is the atom getting bigger or smaller?
Bigger.
It's getting bigger, which means that the electrons on the outside are farther from the nucleus and they are easier to remove. Okay. So bigger atom, lower ionization energy. So the big Fresno Fair was held recently, and people asked me, well, did you go to the fair? And I'm like, I haven't been to the fair since back when I only had 2 children, because I only have 2 hands, right? You go to the fair, you got 6 kids running around, you're going to lose one, maybe several, right? So there's me, big family, 6 kids. It's easier to snatch one of my children, right? Then if I'm a small family, here's mom with 2 kids, and I'm holding on literally to each of them, you're going to have a hard time pulling one away, right? So small atom, high ionization energy, right? It's harder to take the child from a small family. Easier to take one from a big family. And just to say, I have not lost any children for more than a couple hours. So they're all still safe and good. We see that the first ionization generally increases as we go across a period. So that's going from lithium to neon. We see it's actually a pretty big jump, isn't it? The ionization energy is increasing. Well, what's happening to the size? When we go across, the atoms are getting smaller, right? Harder to take electrons from a smaller atom. Okay? So going across, we see increase in ionization energy because the size is decreasing. Coming down, we see a decrease in ionization energy because the size is increasing. So ionization energy and size, the trends are exactly opposite to each other.
The gap in the middle.
What's the gap in the middle? Those are the transition metals.
Oh, okay. They just cut those out.
Yeah, they just don't follow very nice trends. And in Chem 1A, we can ignore inconvenient truths. Yeah. So here, determine the element in each pair with the higher first ionization energy, if possible. So let's look at tin and iodine. So here's tin, and here's iodine. What I would ask myself first is, which one of those is bigger? Which element is bigger? Which atom has a larger size? Tin or iodine? Tin, because as we're going across, the increased effective nuclear charge is pulling everything in, and they're getting smaller. So this is bigger family, smaller family. Who is it harder to take children from? Small family. So we would predict that iodine has a higher ionization energy than tin. I'm make sense? Let's do one more. Let's do D, fluorine and sulfur. So here we got fluorine, and here we got sulfur. When we were looking at size, we saw one that was a diagonal where the trends were opposing each other, and so we said, well, it's not really possible to tell. Here's another diagonal one. So again, I like to think about the size first. So if I'm going across, that predicts that sulfur is larger, fluorine is smaller. Going across gets smaller. And if we're looking at the vertical trend, going down gets bigger, sulfur's bigger, fluorine's smaller. So both of those trends point to fluorine being smaller. So which one has a higher ionization energy? Fluorine. Small family, harder to snatch a child. It's not very PC, but hey, if it helps you, go ahead and have a laugh at my expense. It's fine. Of course, if we're going to have trends, there have to be some exceptions in the trends. And these are a little bit interesting. There's an exception between group 2A and group 3A. So going across, we expect that the ionization energy would get larger, and yet boron has a smaller ionization energy. So what's going on here? Well, here it's helpful to look at the orbital diagrams to see, well, what exactly are we losing? I'm going to put boron over here and beryllium over here because that's where they are on the periodic table. How many valence electrons does beryllium have? 2. So those are going to be in that 2s orbital. This is 2p. And how many valence electrons does boron have? 3. 1, 2, 3. Again, this is 2s and 2p. So when we're ionizing beryllium, we're removing a 2s electron. The first ionization energy for boron is removing a 2p electron. This room here costs more in the hotel. This sublevel is higher in energy, it is less stable. And so it's easier to take this one away than the 2s, and that's the reason why there's this zigzag in the trend. We go back here. What we're seeing is right here. So in each of these, there's that little jog, right? Where we would expect it to be going up continuously, but it actually goes down briefly. And that's because here we're losing a p electron instead of an s, and it's just a little easier. The transition metals are just a big mess, yeah. There's another exception between 5A and 6A. So here's nitrogen, group 5A, oxygen, group 6A. Orbital diagrams. So for nitrogen, I'm losing an unpaired electron. This sublevel here is exactly half full, and that's kind of like a bonus situation. There's a coupon that saves you on the hotel fees if you have half-filled or completely filled rooms. Down here, this is not exactly half full, and when I'm removing this electron, this is a guy that, I mean, just in my characterizing of atoms as having personalities and stuff, this guy's just not really happy anyway because he's got to share a bed, right? It's easier to remove this electron than one of those. And that's why oxygen has a lower first ionization energy than nitrogen. Another thing we can see is that, as I mentioned before, you remove one electron, there's a cost. The second electron's going to cost more. The third's going to cost more. But it's not even stair steps. you see some pretty big jumps, right? Sodium has one valence electron. Sodium has one valence electron. So we remove that valence electron. When we remove the second electron now, that's a core electron. That's in a lower level. It's more stable, and so it's going to cost a lot more to take that one off. Magnesium has two valence electrons. Lose the first one, lose the second one. It's about twice as much as the first one. But then you go to the core electrons, and the price shoots way up. So this is kind of a weird looking graph.
Is that in joules or?
That's a great question. What is the unit on that? I'm guessing it's joules. Yeah.
Oh, on the side, I think it's
Oh, kilojoules per mole. Cool. Kilojoules per mole. Good question. So sodium has one valence electron. You lose that. It's okay. The next one's more expensive. Magnesium has two. How many valence electrons does phosphorus have?
5.
5. So here's the first one, second one, third one, fourth one. The price is going up, fifth one. And then after we've lost all the valence electron, the price goes from 6,000 to 22,000 kilojoules per mole. A huge leap, because now it's getting personal, right? Took the ones off the outside, not a big deal. But now the ones that are really close, that's going to be bad, okay?